here is the line segment. And we grab the, what is this, the compass, and we open it up. The distance doesn't matter, but it should be more than half. And then we stick it in one endpoint and we draw a circle. And very importantly, we don't change the distance, and we stick the needle into the other endpoint and we draw a circle with the same radius. And now look at the intersection points. The intersection points are on both circles, and that means that whatever the radius was of these two circles, this distance and this distance are the same. This point is equally far from the two endpoints because we used the same radius, right? This is R and this is R. And so is this. And guess what? 2 points uniquely determine a straight line. So we just connect the 2 points. But it's really cute that if someone says construct a right angle, we cannot do any less than a perpendicular bisector. So if someone says construct a right angle, you would construct a perpendicular bisector and say, ignore the rest, here is your right angle. Okay, so we do it one more time. Now, theoretically, I should write down the steps that we put this needle into one end and draw a circle, and with the same radius, we draw a circle centered at the other end. I just don't want to slow down this class with the writing. And then, as long as we use the same radius, these 2 points are equally far from the 2 points, and that is your perpendicular bisector. But you know, constructions, this is the most basic one. There are many, many things that we do in one picture, in one construction picture. So usually what you will observe is that we don't draw the entire circle, just the part that we anticipate we're going to be using. So we don't just draw the whole circle. Well, this is a little bit too small. Just the part where you kind of guesstimate where that perpendicular bisector would go, and we just draw that part because otherwise the picture would be a little too busy. But now it's more mysterious why it should work, right? They don't look like two circles anymore, but that's what it is. That's what a usual construction looks like. We just draw the part of the circle that we want. Now, there is this really, really cool website I want to show you. Let me find it first. This is fun. Actually, this is a website called Math is Fun, and in this case, I have to agree wholeheartedly. This is a really, really cool website. All right, so here are the basics: line segment, bisector, and right angle. This is gonna work, yes. So here is the little movie. And so here is the line segment, and we're gonna construct a perpendicular bisector. So there we open up the, there, that's the most basic construction. So you can watch this anytime. And there is a whole long list of really important constructions, you know. They also have given the 3 sides, but with the 3 sides, I have an issue, is that the 3 sides should have been given as line segments, not as numbers. What is the triangle? Copy a triangle. I think this. See, there is a lot of really good little. Oh, there it is. I knew it was somewhere there. So I don't like that these are the numbers that are given. It shouldn't be. It should be 3 line segments drawn. Oh, maybe I should push play. See, this is not allowed. Marked straight edges are not allowed. So here is one side. I think they two start with the longest one. That is Thales' theorem. And that's in the book, actually. If you look at the first section of the trick book, the Michael Corral book, the one I'm praising, it's right there. So let's start with a circle. We can actually use a pretty one. No, never mind. I'll do that later. So I need to find the center. What's this? No, I lost it. Okay, so it's very important that this is a diameter. Okay, so this is the picture. I like C for center. Okay, and so because we are in a circle, there is going to be a lot of isosceles triangles. See, these two sides are equal because they are radii in the same circle. Therefore, these two angles, I'm going to call it alpha, are also equal. Does that make sense? Isosceles triangles, equal angles. And we're going to do the same argument on this triangle, where these two red sides are also equal for the same reason. They are radii in the same circle. So these two angles are also equal to each other. And now we're going to state that this big triangle ABD, that if we add all the angles, the sum is 180 degrees, which goes like this. The first angle is alpha, the second one is beta, and the third one is alpha plus beta, and that all adds up to 180. And then if you look at the left-hand side, we just have twice alpha plus twice beta is 180, which means that when we divide by 2, we get alpha plus beta equals 90, which means this angle here is right. And Thales' theorem is about this, that if you have a triangle where all 3 points are on the circle, on the same circle, and one side is diameter, that's a right triangle. That's a huge, very, very important theorem that is being ignored nowadays. No one wants to reteach high school geometry, but it's such a tragedy. So I'm going to give you a definition first. Given a line segment AB, its Thales circle is the circle of whose diameter is AB. You can think about how to construct it. If I give you a line segment AB, you would have to construct the perpendicular bisector so that you find the midpoint, and then you open up the compass, and you draw it. That's the Thales circle for a line segment. And now here is Thales' theorem. Even line segment AB, triangle ABC has a right angle at C, if and only if C is on the Thales circle. So what that means is that if you have a line segment and you want a right triangle, well, if the right angle is to be here, that's easy. If the right angle is there, that's easy. But what if you want the right angle to be at the third point? Well, all of those points are on the Thales circle. And it's pretty straightforward. If you move outside, those angles are going to be less than 90. And if you move inside, those angles are going to be more than 90. But if you want exactly right triangles, that's the way to go. They are all on the Thales circle. That's Thales' theorem. Any questions?